this is not the deformation lemma that I need, or I would need this, and it's probably in order 0. And if I, as I told you yesterday, if I want to just pursue the proof of the Mountain Pass Theorem, as Ambrosetti and Rabinowitz did, as an analyst can do, I could just use that lemma, assuming that I have access to this infimum. But I only can have access to that infimum within ACA 0. So, because ACA 0 is capable of saying that such a thing exists, and then I could use it. So, we want to push down the proof to Wiconik's lemma, so we want to avoid talking about that thing as something a priori. So we have to change a little bit things. To remain in Wiconik's lemma, we should not treat this C star as an existing real, but look for other tools to allow us to prove the existence of real that once we found happens to have these features of the infimum. We begin with our main result, which is a very cool one, which says the following. So the following is provable in Wiconik's lemma. Let H be our separable Hilbert space, and I our C11 functional. We suppose that I0 0 is 0, and that the GH, the geometrical hypothesis that I told you about yesterday, are satisfied. We consider this notation, the C of G is just shortened for this maxima of the decomposition, and I always have access to that in Wiconik's lemma because even G, because G is continuous, I is continuous, decomposition is, and Wiconik's lemma gives me access to that kind of maximum. In gamma, which was my space of continuous paths from 0, 1 to H. Then for every real epsilon and for all path in gamma P, there exists another path and a member U in the space such that these three things. So I prime of U is less than epsilon. We have this difference, and we always can find Q less the C of Q less than CP. This will be a lemma that will allow me later to form a Alice-Mail sequence. But the proof of this theorem is interesting by itself, and probably this is the most interesting part of the forward direction. Because, let's say, the sketch of the proof. First you have to notice that for all G in gamma, for all path, we have that the C of G, the maximum of I of G of T, is greater or equal than alpha. Alpha was this number that we have in our geometrical hypothesis. How do I prove that? This is very easy, and I just want to put it as an example. I won't do the entire proof because it's very long, but I want to assess the following. Let me. So proof of this part. Let me claim. My first claim 0 is for all G. C of G is greater or equal than alpha. So first, we have that G of 0 is the norm of G of 0 is 0. This is how I should fix my G and have this. The norm is 0, and also, of course, the one is B because how gamma is defined. But remember that one of the geometrical hypotheses was that this has to be greater than some rho. which is greater than 0. So I have that the function, this composition of G with the norm is from 0 to something greater than 0. So by intermediate value theorem, which is provable in RCA 0, there is some G of, in this case, well, depending on G, in thank you. In 0, 1, such that G of TG is exactly the value rho. But if you recall the other part of the geometric hypothesis, whenever I have this, is a geometric hypothesis, part of the theorem, the image of that, whatever the vector is here, has to be bigger than alpha. So I found one bigger than alpha, then the maximum, which was the C, has to be. Just wanted to point out that we are using the geometric hypothesis there, and also some form of intermediate value theorem. For an analyst to have this function, the max of I would be enough, because I am, and this was for all G, so I am bounding this from below, so it would be enough to say that the infimum exists. And they will do that, just prove this, use the infimum and have the theorem. But I cannot do that, because I will need ESI 0. But it's important that I have it for other purposes, but also to see that the proof that will come now, it's longer, because I cannot do what in the meta language I can. Now, to prove, let's see again this. For all epsilon and for all p, there exists q, there exists u, such that tin. So I will prove this by contradiction. I assume the existence of epsilon 0 and p in greater than 0, a p in gamma, such that for all q with CQ less than CP, and such that, and for all U in these different sublevels, we have I prime U is greater or equal than sigma, that epsilon 0. It's clear that it's a contradiction. I'm just saying there exists one that satisfies two, but not the first one, the regarding the derivative. This is well, it has to be non-constructive, the proof, and most of the things that we will use depend on having this kind of proposition. So first, we have to prove each of the following claims. First, that this thing holds for any epsilon tilde less or equal than epsilon 0. So just, we are saying that I think I will be using again and again, so you can, but only one, this one, so. But I can okay. I can do the thank you. So, well, this claim I won't prove, but it's very easy to prove. Like, this claim, this star proposition holds for any smallest. than the one that I'm claiming by contradiction exists. So I have to particularly take this will be just for some purposes that we won't talk about. I will take this, the minimum of those, the epsilon tilde, and I will take another one just called epsilon that will be strictly less than epsilon tilde because it will be its half. So just have in mind that epsilon and epsilon tilde are fixed. Then I have this one. For all q in a path such that C of q is less or equal than C of p, I have a deformation such that A and B hold. So this will mimic exactly the proof of the original deformation lemma. But instead of talking about the C as a critical point, I will talk about C of Q, precisely the maximums of I of Q of each Q given there. So of course that eta, that deformation will arise from my version of Picard's theorem about EDPs. That's the real problem. Like that is when I should use that version of Picard's, and I will do it like just a part of it to show you why I need some of the hypotheses I have put in the theorem. So this is the claim 2. So the idea would be to define the function, the flow, like the solution of of an IVP as that somehow will also have these characteristics. So the idea is the following. So define this set A and B this is exactly. So one thing you can automatically see is that these sets have no intersection, have intersection the empty set. And now this will be necessary, but just to now define also, we're going to define a lot of functions, but I will say just the important things you have to know about these functions. So I take X and is if I am below C, is if well, what is C here is really just to this is notation. For now, C is just my CQ. Avoid writing it. So important thing that it's very, since I we assume to be C1, we can prove that it is locally Lipschitz. That is a more or less basic thing of analysis, but you can find a effective proof. So we can prove that any C1 functional is effectively locally Lipschitz. So this will make this as just a linear combination of it also locally effectively Lipschitz. This, of course, too. And as being this was defined, also will be locally Lipschitz. Then, if I define G as this function, because the minimum, the maximum, the constants are also effectively locally Lipschitz, this will be effectively locally Lipschitz too. And also has the property that it's bounded for all x here. But yeah, perfect. This, I think. So, and also it has some properties. G hat. Sorry. No, like what? Don't see. Ah, no, maybe you're right. Exactly. And then this is exactly this part that we. Exactly. Yeah, the idea is more or less. Let me recall. Ah, yes, yes. No, this is plus. But exactly. No, no, this is exactly. No, I have the proof that it's continuous. Yeah, exactly. Like, sorry. Probably. I get my continuity. I get my function. Yeah, this was this we were talking about, like using I to, because well, just to say it, in the classical proof they use some kind of distances between sets that is ACA 0, so we have to make an arrangement, but it was just about getting the right coefficients. Yeah. So because the idea, I should start with this thing. We need a G that is effectively locally Lipschitz, that is 0 in A, G is 1 in B, and that it's bounded by 1. One way to find this G is using distances, but we realize that just finding the right coefficients will do it. So, to also just define H such that does do this. H of A's will be also, this will 1 if S is here, and 0 if it's here, and 1 over S if S is greater than 1. This is also locally Lipschitz. Why I do need this? Of course, this is tailor-made to, when doing a lot of math, have this access to these properties. And finally, I define this. I think this is better. W of x minus gx h of the norm of I prima x and I prima for x in my Hilbert space. The only thing is locally Lipschitz bounded by 1. One of my hypotheses was that I prima was locally Lipschitz here. I use that. I need that. This is locally Lipschitz. You can prove that compositions, products, etc. remain locally Lipschitz. So, like, yeah, this is effectively locally Lipschitz. So, this problem has a solution unique because of what I told you yesterday. So, has a unique solution continues in both of the arguments. Thank you to Picard. So I need, because the only thing, of course, you can also prove that this local Lipschitz and bounded by 1. So it has all the requirements that that version of Picard's needed. And yeah, just wanted to explain how we get our deformation. There is a lot of, not complicated, but calculations that make this possible. That kind of thing, because of how it was made, will have these things. But that is made in even, it's just copying and pasting the original proof, because it's only about using derivatives and chain rule and cool stuff, but also the fact that this is unique will give us this. Because, you know, B, what it's saying is that for this set, for this use, this remains stable. This is constant. This doesn't move. But it's not important. I just wanted to focus in the part that we say this is why I need Picards. Perfect. Let's continue. Claim 3 of the proof. For all q in gamma with CQ less or equal than CP, there is some q such that some q tilde such as C of q tilde is less or equal than CQ minus epsilon, which was fixed. To prove this, consider this notation. We already have access to that deformation, eta. Just consider the notation just to unpack it, and define q tilde by the composition with q and eta 1. Here is where we need that it needs to be continuous with respect to the second variable, the eta. So that q tilde will be also continuous with respect to the second variable. And we can also use properties of the deformation to show that precisely that q tilde is in gamma, which is important. Being in gamma just means being continuous and to have q eta of 0 is 0 and q eta of 1 is b. And it's also not trivial, but fairly simple to prove that we will have this inequality. So we have found this. This is just, the cool thing is that we are just arranging a little bit the original proof of the theorem, but instead of talking about a C that is already a non-critical point, just this C of Q. So if you see, yeah, thank you. So that's my claim 3. So, well, eta is follows from, so it's just a continuous function such that this happens. And I just like, I do all this construction, but then of course I have to do a lot of math to really prove this. But that is analysis. That's it's a deformation lemma. I prove that this kind of deformation exists. Okay. And then using that eta, we can prove that the q tilde is also in gamma and has this property. But look at claim 3. So let's go to claim 4. If I apply it starting from q, like q0, and then apply it, I can form a sequence of elements of gamma such that every one of them is less than the other one, with this epsilon fixed as the difference. So it's obvious that eventually, if I am going back by a down by a fixed thing, I will eventually find some n which will be less than alpha, which is a contradiction because I already proved that it cannot happen. So that's cool. The cool thing is that we should, well, this, maybe I was going to talk about the, yeah, exactly. When constructing this sequence, we need to use sigma 0, 1.
I mean, to show that
But I think you have need the infinite sequence.
sure.
In this case, no. No. We are in gamma, not in the cross Cantor base. Then we use that. I think this, we need
You don't need the infinite sequence. So you know alpha, so you know after how many steps.
yes.
In this case, you actually need to.
But I think we
Probably you
can,
can do by
but no, the G's, I need to have access to that maximum. The G's can, of course, are uniformly, or can be, I can give the modulus of uniform continuity. But when composing with I don't have more information. I need the maximum of I of G of T. So in a general sense, I cannot know. But if
do that assumption. For ellipses.
what?
If it's just globally.
Which ones? The I. But
Made a uniformly on the
yes. I don't know because I did it for global ellipses, but global ellipses is a too big assumption for I mean, and also one reverse. So it's RC because it's RC0. I mean,
Probably would also be
but we have the composition of G and I will be remain uniformly continuous. In that case, because it's the only. I'm thinking. Yeah, let's see if I use weak conics in a different situation later. But well, I have this. So now the MTPT finally. The following is proving Urkonix lemma, maybe just RCA0 if we say that uniform continuity is given. Suppose all my hypotheses, my conclusion is there exists a point which is critical. I prime of x star is 0. And this is how I have to change the statement. I of x star is 1, lower bound, and 2, the greatest. In other words, is what I mean from an infimum, so C star. How do I prove this? Is just first let P0, P1, P2 be an enumeration of A, which what I am saying that this. My countable then subset of gamma. We define this Qn taking for each n Qn equal to Pi if Cpi is the minimum of the j's less than n of Cpj. Record Cp is just the maximum of I. So the only thing that I'm doing with that is making the decreasing sequence of reals Cqn. It's making this sequence of reals a decreasing one. I use for all of these, for each Qn in gamma, defined that way, the previous theorem. So it will give me a q tilde n in gamma and an xn in h, such that these three things happen. It should be clear that the first one will give me that I prime xn goes to 0. Yeah, it's very clear. It's converges to 0. And also using 2 and 3, it is possible to prove that I of xn is bounded. So it is a Palais-Mail sequence, but I have my magic card, which is the Palais-Mail condition, that will give me a subsequence that the convergence, and it's very easy to prove that the limit of that subsequence is a critical point. And then I prove that the image of that critical point is exactly an infimum. So I have a real, this image, that appears to be an infimum, but I proved that afterwards, not as in the classical proof that they assume it a priori because they can. I put simple and beautiful arguments of real analysis. They are really simple in the sense that are canonical, because it's when you do that, then you feel like you are doing analysis in the sense that you do a lot of triangle inequalities and cool things, and you feel like you are doing real math. But I'm beautiful because of that.
Well, you've been doing real math.
Yes, I haven't. This is not logical. The reversal, which comes now, this will feel logical now. Because you have been.
That's also real math.
Yes, it is. Oh no, it's what was the joke? It's complex.
Is this about the funding?
Cool. So it just feels romantic to optimize the proof that should be ACA0 and prove it and make it Wiconix lemma, but we haven't optimized it yet because we haven't proved the reversal. So let's go. For the reversal, to prove that ACA0 goes, assuming the MPT will have the Wiconix lemma, we do a contraposition. So we assume that Wiconix lemma doesn't hold, and we will prove that the MPT doesn't hold. So, what does it mean that the Wiconix lemma doesn't hold? That there is an infinite binary tree with no branch. The first part is just following some construction that Simpson already does, so maybe you are familiar with this. It's just refining it a little bit. So, we have my infinite binary tree with no branch, and I denote by T tilde the set of falling leaves of the branch, which is just defined. We have a sequence in T tilde if it is not in the tree, but all of that is down it is. This is just a definition. We will define just the covering of the Cantor space. As usual, for this I will do a proof of by graphics, which will be more clear. But it should convince you that the procedure is computable. So let's do this. So we will have my tree T, and we will enumerate level by level the fallen trees. And then we will calculate these two numbers, which are just intervals of that define the Cantor trajector set. And then we will join, and then we will define the function I, taking the length of the sequence of U and defining it as the middle point. And then joining these middle points with a continuously differentiable piecewise sine functions, which is a computable thing, so we can do. I really think the best way to show this, and that should convince you is computable, is just an example. So let's have our tree. That's an example of a tree. You should imagine it's infinite and it has no branch, if you can imagine that thing. So well, first level, nothing, and I will go in level by level. So I go zero level, first level. I don't see any fallen leaf. The black one is the tree. The other one is just to see the fallen leaves. Then I go to the third level, to the second level. 0, 1, 2, yeah. And I find the first in the left, the first white ball node is a fallen leaf. And I see that fallen leaf, I calculate my Cantor interval, it is this, and I put, for my function, the length was 2, right? So 2. For now, just make it the line, all the interval. Then I go to the second fallen leaf, which is this, that is the 0, 1 sequence, right? And it is about this interval, and I put 2 also. Now, that would be my function for the second level. Now I go to the third level. There's another fallen leaf, yes, that one, the last one on the right. That corresponds to this interval. So I put I of this interval in 3, right? Up there. And then I will go to the fourth. And then I will go to the third, etc. And the important thing is I never will read of fallen leaves because it has no path, this tree. So I will always be able to do that. And also it's infinite. So I will be defining it step by step in a way that it's unbounded. So this idea of symptom to prove precisely that Wiconic's lemma is equivalent to every function in the 0, 1 is a continuous function, it's bounded. But we make you don't need just imagine if I, of course, I have this. If I put lines, straight lines between them, I have a continuous function. But I don't just need a continuous function, but a C1, C11, and Fales mail, and a lot of things. So we do that, right? So imagine that, as I told you, like in the middle points of each of the intervals of the Cantor space that I'm doing, I put the length. And then I zero it, and that middle point is, they are joined with the sign, with the quarter of a sign. This is the quarter of a sign. If they are of the same height, like these ones, I put the entire wave, the half of a period of sign. And also, if I have these ones, I just do it. The idea is that sign, yeah. It's like, it's the, my f of x is a of period x minus h. This, and I can always, because if I know that I of 0 has to be 0, and I know the length. If you know which point you want to join, you can use that beautiful formula of the. So at the center point, all it has is the correct value. Yeah, the idea is that it is made to collide, so it's continuously differential. Not only differentiable but continuously differentiable. Like probably, like if I have this sign, I want to collide it with another one. Like it should be like this. So it is the when the maximum of the sign is, and the one that I colliding with is maybe is another one. Maybe goes like this and this, but this is. So I make it. I force it when colliding to be continuously differential in all of those paths. Which was important, right? It has to be C1. And from here, for the left, it's just the parabola. It's the left branch of the parabola in the vertex. So still continuous. I also will need a B. This will be my B. Also, this is the other sign, but this is also a branch of a parabola in the vertex. So you have a C11. Also, the geometrical hypotheses are hold because, well, this is a minima and this is a minima, and it should be easy for you to see that if you have two minima, it's just a particular example of those geometrical equations. So, yeah, what else we need to our function to have is Balismail is a difficult one. So first, it also has to be C11, right? Locally Lipschitz. But like the blue one is I just grabbed the derivative. Just for you to see that it's in real continuous. Because only cosines, the blue one are cosines, the pink one is sines. So if here in the step is indeed Lipschitz, not only locally, but because it was it's like infinite unbounded function, we can just argue that it's locally Lipschitz. And then the Palismail condition, which it's the following, right? We need for the Palismail condition. We have time. So let xn r such that the prima of xn goes to 0 and the phi of xn is bounded, let's say by some n. Then I should show that this has a this is a Palismail sequence. I should prove that this is it has a convergence subsequence. But the idea of the proof is that I can take this is just the derivative, the prima. And it serves as an example. Let's say that we bound the I, and we also have this part. We can, in a computable way, check if each of these xn, like is near of each of the, because the important thing is that the zeros of the function, the blue function, we will be checking each of these elements, how near they are. So we are, in some sense, it has its nuances, I think, taking this infinite sequence and putting in these finite boxes, which represent each of the zeros. No, I can build the. Yeah, indeed, we can prove that because it's like arguing that there is a computable form of. I can. Because we find a procedure to put it like. I should write the procedure. Maybe if I think I have time, right? So like computably it's like this. Like I need a procedure to do like this. I will define. How I will first define. Yeah, for each first like let mi enumerate the points such that I prima of mi is 0. I am just enumerating the zeros of the blue function. But of course finite. And we check computably if let's say stage. I do it by stages. Check if we'll do some. Well, sorry for not using the water. Check if for k I don't know if this is going to be understandable, but we will check for each of these elements how close it's to each of the zeros of the function. And if yes, we put it in we define the, let's say, I'm given a version, so the n+1 step will contain this new one. And if not, I just remain as I was. This is, and I do it for each of those. So I am just, for each of the finite points where we have the zeros, checking if, checking if I can have infinite there. So my claim is that there is one that is infinite. Like, well, I should put like define. This is the procedure that defines xi as the limiting process of this computable procedure. And my claim is that exists the I such that xi is infinite. And then this will be a subsequence that converges to that point. If not, this thing, which means for all epsilon, there is an n such that I prima of xn is less than epsilon, will give me a contradiction because in some sense I am taking an infinite set such that and putting in finite boxes, and it's just the use of pigeonhole. And because I know the bound beforehand, is computable. It has its nuances. I don't know if I will finish why this is a counterexample, but it meets the Palais-Mail criteria, but it's just pigeonhole indeed, or at least my proof has the use of pigeonhole. I think you can do different versions, but yeah, trust me that this function, well, not this function, this one has all the criteria, meets all the hypotheses. Now I will show that it has no thesis, but it's very simple, right? So what is the thesis? That if I join all the paths that go from 0 to b, this will be my b, which are, there are no other paths that the graph of the function itself, which was unbounded, because you don't see like this one. This is just the stage 3. The real function is an unbounded one that goes. This doesn't exist. So no point can have its image. So no point have the info of that as the image. And that's the story of the reversal. The most difficult part really is the Palais-Mail, but I'm sure that the pigeonhole principle does. And that would be all. I think I am out of time. So philosophical considerations for another time. Thank you very much.